Welcome everybody. Glad you can make it to the first session. I know it's hard to get up early in the morning and come here. So I'll be talking about Scout, a work we did at LinkedIn. Again, I'm a senior staff engineer in the performance team there, and I work on trying to figure out how to make LinkedIn fast using whatever way we can. This work was done at LinkedIn, joint work with a lot of people at LinkedIn. Mostly data science folks, bunch of data science folks, bunch of network operations people, and performance. And we would actually, the reason this work happened was because we were trying to solve a real practical problem. And just so happened that we had good people who could work on this problem, find a solution, and we thought it's a good problem and solution statement to present to the research community, network performance research community. Quick disclaimer, the real author of the paper, the person who did most of the work is Yang. Unfortunately, she couldn't make it today due to personal reasons to Greece. So you get a poor substitute, that's me. Which leads to my disclaimer that bunch of statistics, data sciencey stuff, I'll not be going into depth of because I'm not an expert there. I know very well about performance, real user monitoring data. I can motivate the problem very well, so hopefully that is a takeaway for you guys to figure out, what is the problem, why it's an important problem, and what as a high level, what we did to solve the problem. All right, so before we start, let me give a quick overview of how LinkedIn's page serving pipeline works. It's not just page, it's also for mobile apps. When a user accesses LinkedIn.com, we actually serve the dynamic content from our data center, and dynamic content means HTML of the page for web and JSON or whatever format we send the data for mobile apps. And the static content is served by a third-party CDN. So static content meaning images, JavaScript, CSS, and so on. As you can see in this picture, there is a middle proxy which we call POP that helps us improve performance. So I'll go about why that helps, right? POPs, full form is point of presence. They are nothing but just reverse HTTP proxy. And we try to push them as close to the user as possible because we cannot have data centers everywhere. So these are cheaper ways to make the site faster. And why exactly do POPs help? Let's go over that quickly. All POPs do is they do a early connection termination of TCP, early TCP connection termination, right? So let's imagine a world without POPs. We'll have a user trying to access LinkedIn.com, assuming the user is far away place with a 250 millisecond round trip to our data center in US. So the connection establishment will take 250 milliseconds. Browser would send a HTTP GET request. The data center will flush the head as soon as possible. That will result in 250 millisecond of first byte time. And then server will take its time to build the rest of the page because this page is usually personalized. So it's not available readily to be served. It's personalized on a per member basis. So the data center actually does some computation, figures out what data to show to the user, and that takes some time, right? And once the page is ready, it's around 60 to 100 kilobytes compressed. So because of the way TCP works, because of we all know congestion control, initial congestion control is only 10 segments. Between 60 to 100 kilobyte is what our payload size is, so it takes around 3 to 5 round trips to actually send the data back to the user because of again the way congestion control works, right? So if you add this all up, ignoring the server computation time, only just transmitting the data itself is taking 1750 milliseconds when the RTT between the user and the data center is 250 milliseconds, right? Let's change the situation. Let's introduce POP in between. Again, POP is nothing but reverse proxy. So pushing the POP closer to the user, it's only 100 milliseconds away now. So right away you see connection already, because connection terminates at POP, you already save some time there. Connection is terminated at the POP, so only 100 milliseconds there. First byte will still take 250 milliseconds because it has to go all the way to the data center and send the data back. But here's the interesting thing. In this case, even a 60 to 100 kilobyte payload is sent in one round trip from the data center to the POP. That's because POP and data center are talking to each other all the time, right? They have keep alive connections. They have big congestion windows because the POP is serving millions of users. So they're talking to each other. Congestion windows are huge. You can send the whole data right away from the data center to the POP in one round trip. And of course, POP, when it sends data back to the user, it takes 3 to 5 round trips again. But these 3 to 5 round trips are only 100 millisecond long in terms of RT instead of 250 millisecond. So if you add all this up, now it's only 850 millisecond, and that's a clear gain of 900 millisecond, right? So that motivates us that POPs are important for performance. And we actually did some study. We built some POPs back in 2014. We published a blog on our LinkedIn Engineering blog that shows that using POPs and actually just the assignment of users to the right POP, optimal assignment, gives us anywhere from 5% to 25% improvement in page download time. So hopefully that motivates the importance of POPs. So clearly, like to improve performance, that's my job, right? I recommended to LinkedIn that, hey, let's build more POPs. We'll easily get 10 to 25% improvement. Unfortunately, POPs are not cheap to build. Our previous experience has shown that there's a capex of around $1 million for building the POPs the way we build it. That's a one-time cost, and OpEx regular cost is, it can be up to 700K US dollars per year. So they're not cheap. So you have to be prudent in picking, where to build the next POP. And that's basically the problem statement for Scout is, how do you select where to build the POP, right? And there's some particular considerations in picking a location of the POP. We don't want to go and build our own buildings and real estate for POPs. We do it for data centers, but not for POPs because that just adds to the extra cost. So we would rather just go to an existing facility and install our servers there. So we need to figure out where the facilities are, whether they pass our criteria like power requirement, peering density, availability of transit, and things like that, right? So that already is a consideration. We obviously want to build a POP which is the best for our users. So we want to increase the number of users that get impacted from building that POP. But not just that, we also want to make sure that there's significant improvement in performance for those users. So for example, LinkedIn has a lot of users in US, so we can keep building POPs in US, but that doesn't help after a point because we already have enough POPs in US. So the improvement going forward for new users, for new POPs is not that much. So again, that's the problem statement for Scout is given a set of existing POPs, where should we build the next POP? Where should the next POP be, or 1 or 4x number of POPs? So the high-level methodology of Scout is we shortlist locations by our requirements of the facility, and this is up to each person, up to each company, what is the shortlist they want to pick. Then we want to rank these locations by some metric, and the metric we picked was something we called impact score. For each location, we predict the impact score of building a POP in that location, and then we just rank these locations by impact score. And what is impact score? It's basically the two earlier considerations we talked about. What will be the estimated performance improvement of building this POP for a given set of users, and then how many page views extra we will actually impact using this POP. Okay. Here's a concrete example of what I mean by impact score. Imagine that we had a POP in Florida which was serving Brazil. Let's say we have a candidate POP location in Sao Paulo. If we build this POP, after rerouting all the Brazil traffic to Sao Paulo, the median download time might improve from X millisecond to X minus Y, so there is an improvement of Y millisecond, right? But Brazil traffic only accounts for Z% of LinkedIn traffic. So what impact score is finally for Brazil, for building a POP in Sao Paulo will be Z into Y, right? And then we just sum up all the impact score for all the regions that will get impacted by building a POP in Sao Paulo. So that's straightforward. What is missing here? What's unknown is estimated improvement by building this POP in Sao Paulo, right? Like that's the hard problem. Everything else is straightforward. So let's see how we can estimate what will be the improvement by building a new POP. The previous works that have done estimation of round trip time, RTT, for a given location. So given a user distribution, given a particular location, they try to estimate what will be the RTT to that location. That doesn't really work very well for us for various reasons. One, our actually metric that we want to optimize for is not RTT, it's actually page download time. And the page download time, the size of the page actually depends on the user characteristics. You can imagine a user who is new to LinkedIn may not have a lot of connections, so their size of the page will be smaller. If you have a lot of connections, then we have more content to show you, so the size of the page will be bigger for you. Also, TCP congestion window and control state depends on the user also, like how active the user is on the site. That will define congestion window size, right? Using RTT, you can only estimate the first transmission of the page, but if the user is interacting with the site again, congestion window can be at any state. And also, another requirement we had was we didn't want to invest too much time in active probing, active measurement. We wanted to do it based on passive measurements with as low cost as possible. So that's where our solution was to try to build a statistical model of page download time given some data that we already have. And let's try to see whether we were successful. So the data that we used was real user monitoring data. Hopefully most of you are familiar with RUM. It's basically based on navigation timing API, which is supported by most of the modern browsers. And RUM data is actually collected already by most of the web companies because it helps us monitor the performance of our site for our real users. So this is already a low-cost passive measurement data. And what RUM data can give us is information like client IP address, obviously where the user is coming from, and that we can translate to a geographic location using some geo-IP databases. But it also gives us interesting metrics like connect time, TCP or SSL connect time, first byte time, download time, and like if you combine all these three together, that is our metric that we want to optimize for. It's the sum of all three of them that we call page download time. All right, so we figured out, okay, we want to try build a statistical model. Is it even possible? Like RUM data is notorious for being very noisy. It's long tail, it's from real users, so the data is very noisy, browser implementations vary a lot, things like that, right? So we wanted to figure out whether it's even possible to do it. So simplest way to build a model is linear regression. Imagine on the x-axis you have geographical distance of the user to pop. On the y-axis, one of the metrics, connect time, let's say. And if you just put them, put all the RUM samples on this plot, we can try to draw a straight line. That's your linear regression model, right? So linear regression is easy to do, very straightforward, and that just solves the problem, right? It's right there, we have a solution. Not so easy. The reality is more like this. You actually have, again, distance on the x-axis, connect time on the y-axis, and it's like impossible to see any relation right here. Like, I don't know if you guys can see something. It probably goes down. Looks like as distance increases, connect time actually reduces, right? So that gave us some bad news, but luckily, like, we had nice, smart data scientists with us. They figured out that, hey, if we bucket this data into distance buckets, and then look at connect time, percentile connect times like median, 95th, 75th or 25th, you can actually draw some relationship, and that kind of makes sense. You'll actually see this, as distance increases, connect time is actually increasing. So that gave us some hope. Then they also try to do log transformation. So you can actually, instead of just looking at raw distances, if you actually do a log of distances and log of the connect time also, that actually gives us even better relationship between connect time and distance. So that gives again more hope, but you can see there's like the huge variation. Even given a particular distance, you can see there's a huge variation in the connect time right there. So why exactly is that happening? That's happening because connect time is not impacted only by geographical distance. It's impacted by other factors, and let's list all of this, right? So these are the features to this prediction model. And not just connect time, if you look at page download time as a whole, what are the features, what are the things that can impact page download time? So there are pop specific features. Wherever there is a candidate pop, you have to figure out what is the distance between the user to the pop, geographical distance. That's what we looked at before. But we also have to look at ASN of the user, origin ASN of the user. We have to look at what are the ASNs the pop is peering with, what are the different peers for this pop, distance between the pop and the data center. And then there are other features like which browser is the user coming from, because that can impact page download time. Some browsers may have weird implementations. Whether the user is on SSL, HTTPS, or HTTP. And other characteristic of the user itself, as I said, like if the user is highly connected user, then their connection density is high, so the pages will be bigger and more heavier. Also, it depends on when the user registered. It's not registration time. Basically, whether the user is a new user to LinkedIn or it's an expert user who's been on LinkedIn for 10 years, for example, right? New users will have a lighter page. Expert users will have a bigger page, and things like that. So we try to list all the different features that can impact page download time, and we try to build a model based on that. So after all this, we've kind of proved that yes, it's feasible to build, at least try to build a model for page download time based on different features. So then next step, we try to build this prediction model. And here's where I'll skip over some of the details because again, I'm not the expert. But from my understanding, we tried to do a linear regression, as I explained earlier. Linear regression obviously was not the best, so we did what we call as feature and response transformation, which basically means we took log of all the features and the log of the final response, which is the page download time. So I showed you this graph earlier about log, and that helped improve the modeling accuracy. And finally, we also figured out that that may not be enough also, and then we tried something called piecewise linear spline. Let me just explain what that means. What that means is, so this is the log graph, and if you think about the fitting of a model, we can actually see that between 1 kilometer to 100 kilometers, the model is like this. Between 100 to 1000, the model actually is a little bit different. 1000 and above, the model is a little bit different. So there's this standard technique in data science modeling world, piecewise linear spline, by which if you think your model is not uniform across the data set, you can actually split it based on your feature set. So we did that, and then we had that as a prediction model and we built it, but then we also realized that most of the decisions that we make internally in LinkedIn are based on percentiles, median 90th percentile, right? So there's another technique called quantile regression. Using that, you can build another model for page download time. I'll skip this, but these are basically formulas on how do you actually figure out the model, and then how do you actually figure out the errors of your models. One is OLS for linear regression, and quantile regression is QR. So that's Scout. We selected a list of locations, then for each location we build the impact score. So how do you select the list of locations? Again, this is on everybody's like their own selection criteria. We started with a list of 1400 locations from PeeringDB. We removed all the locations which had less than 30 peering ASNs, and finally we arrived at a list of 400 locations. But again, this is not a one-size-fits-all approach. You can do your own list. I'll skip this because I'm out of time. But this basically explains how to do impact score again, and then we can rank impact scores. So I have 2 minutes left. Let's quickly go over results and evaluation. What the crux of our methodology is the prediction model. So we wanted to evaluate this prediction model. Obviously, it was not practical for us to go ahead and build a $1 million POP and try to evaluate whether our model was right or wrong. So we could not really do that. So what we did was we took data which was used for previous given POP. Let's say we had the Florida POP. We used data which uses data, RAM data that goes to the Florida POP. 4 million of those samples we used. We split into 50-50 into training and test set. Training set was used to build the model. That's how regression works. And the test set was then used to figure out whether the model was actually predicting the actual page download time that we know. This is the result. This shows you 2 different data set. One is what is the prediction error for quantile regression, and what is the prediction error for linear regression, and actually compares these 2 also. So if you actually see, most of the errors for quantile regression was less than 5%, and most of the error for linear regression is actually less than 12%. So overall, it basically shows that quantile regression was a better approach, and it actually works for us because the regression, the prediction error is only 5%. This is probably not useful to us, but it was useful to us. We figured out finally using this Scout methodology what are the POPs we want to build. But we figured out that even though it passes the smell test, the results are not that useful because 3 of the POPs recommended are in India, 4 of the POPs recommended are in East Europe. So doesn't give you a lot of variety. So we ended up doing the same thing for selecting multiple POPs simultaneously. And when we did that, we actually found recent result. India, Australia, East Europe, West Europe, and that's where we actually are going to try to build our POPs. All right, so that was a quick recap, a quick overview of Scout. To summarize, we are trying to solve a practical problem which I think a lot of web companies are facing. We tried to build a data-driven approach using low-cost passive measurements, so there was no sniffing of traffic, no active measurement of round-trip times. Evaluation was done using millions of run data samples. For future work, we are actually right now in the process of building POPs based on Scout recommendations. Hopefully, from that data, we'll get new information and we'll keep improving our prediction model. And at some point, we also want to build a model for page load time, which includes all the content, including JavaScript, CSS, images, everything on the page. So that's it for me. Please reach me at ritesh@linkedin.com or feel free to connect with me on LinkedIn, ask questions if we are not able to answer right now. Thank you.
And maybe we have time just for one question. Oh, yeah.
If I'm not mistaken, I think in your model you consider RUM, which is per user, right? Did you consider correlations between traffic from multiple users? For example, users at a given point of the day, they all together come and request content from your servers.
Yeah, but
does this affect your system, or did you consider it or not?
So we didn't consider that, but I'm curious to know why you think that's useful. Is it because you're thinking the load on the POP will be higher based on the time of day, and that might impact the performance, or do you think internet itself will be more congested because of more users? So we didn't consider it. I'm trying to figure out why do you think that is a useful factor to consider?
I'm not sure it's useful or not.
Okay.
Just asking if it affects it, if you consider it.
Okay. Yeah. So we didn't consider it. Something to think about. Yeah. Maybe. So one of the things we didn't consider was packet loss. And we didn't have, and maybe that's one of the ways we can figure out if there's more traffic on the internet, that might cause congestion and that might cause impact on the page download. So, okay.
Okay, I guess for the interest of time, let's thank our speaker. Thank you
guys.